Standing waves are not unique to just strings. Now strings, we can get a standing wave, but we can get standing waves in pipes as well. I have my ghetto pipes with me today. Terribly high tech. If I have a pipe and I disturb the air inside the pipe, then it will create a standing wave, a resonance inside the pipe itself. Similar to strings, we actually have a relationship that relates the wavelength to how long the pipe is. Long pipe, we get a certain pitch out of it. It's not a very pretty, clean pitch, just because it's a cardboard tube, but it's a pitch nonetheless. Just like strings, if we were to shorten the string, we get a higher pitch out of it. This one's even more muffled, but you've at least noticed the pitch change, right? Okay. The sound in general is higher than it was in the other pipe. So length is related to wavelength, which in turn is related to frequency. But we're going to have two conditions. We have, in the first case that I was just showing you, the pipe's open. Both ends are open. The other end we can close. So we're going to have two situations. We're going to talk about a pipe that's open at both ends and a pipe that's open at one end and closed at the other. Turns out, this end here, even though there's nothing different between the air inside the pipe and the air outside the pipe, the fact that we go from having a boundary, a pipe, to having no boundary, no pipe, that constitutes a boundary. So when the sound wave is traveling through the air, when it reaches this point, the end of the pipe, some of it will reflect back. And that's just because there's something different here. So it constitutes a boundary. This is a free boundary though. It's not rigid. When a wave reflects off of a free boundary, it does not invert. And so it turns out when we have pipes that are open, we have to have an antinode at the end of the pipe. Not a node like the string. The ends of the strings we had to have nodes because they were tightly held down. They weren't allowed to move. At the end of an open pipe we have an antinode. If I have my pipe open at both ends versus closing one end off, the pitch is different. So closing it has an effect. So we're going to look at both types. So one of them is an open pipe, meaning open at both ends. The other is an open closed pipe, meaning it's open at one end and closed at the other. Now, the speed of the wave, this is a sound wave, this is not a wave on a string. The speed of the wave that travels through this pipe is not equal to the square root of the force of tension over the linear mass density, because there's not a string here anywhere. The speed of the wave depends upon the air that it's traveling through. So as we said before, the speed of the wave is going to be 343 meters per second unless we are told otherwise. Okay. Now granted, if you play a wind instrument, the speed of the wave actually changes from when you first start playing to a little while later. Because if you were playing the instrument, you end up filling it full of your hot air. And so increasing the temperature increases the speed at which the wave travels. So if you've ever played a wind instrument, that's why you come, you warm up for a while, and then you retune the instrument. Because the wave's now traveling at a different speed. Okay, let's look at the patterns here. So if I have a pipe open at both ends, I know I have to have an antinode at both ends. So the simplest pattern we can get looks like that. Because it's the simplest pattern, it is called the fundamental, which can also be called the first harmonic. there is a very specific frequency that allows for that to happen. It is called the fundamental frequency. So the terminology we used with the strings is still taking place here. Wavelength. The pipe has a certain length. If we trace this wave from the left to the right, how much of a wavelength is that? 1/2. So the length of this pipe is showing 1/2 of a wavelength. Which means if we solve for wavelength, we're going to get 2L. So similar to the string, the fundamental wavelength is still going to be 2L. We do have an antinode at both ends, but that's okay. It still ends up being wavelength 2L.
In this case, instead of the physical manifestation of the string causing the wave to end, the antinode actually causes the wave to fall over. The antinode is what reverberates back. And the wave kind of follows the antinode instead of the other way, the antinode following the wave.
Yes. So we have the antinodes, it's because of how the wave reflects at the boundary.
But it's the antinode that reflects?
We get an antinode because of the way it reflects.
Oh, okay.
Okay. So the fact that when it reflects off that boundary, it does not invert, is why we get the antinode. So the antinode is the consequence of how it reflects. So F1, we know frequency is speed over wavelength. So speed, wavelength's 2L, so F1 will be V over 2L. When we look at the next allowable pattern, all we do is we add an extra antinode. So the next pattern we can see looks like that. So we get an extra antinode in the middle. If we trace the wave here, how many wavelengths do we see along the length of the pipe? That's one full. We're going from a peak back to a peak. So L is equal to lambda in this case. So lambda 2 is not 2L. Sorry. It is L. So frequency 2 is V over L. Notice, from the fundamental to this second pattern, the wavelength is cut in half, just like it was for the standing wave on a string. If the wavelength's cut in half, the frequency doubles, because the speed of the wave isn't changing. This is called the second harmonic. The next pattern, adding another antinode, looks like that. So now if we trace the wave, we get 1.5 waves. So L is equal to 3/2 the wavelength. So that means the wavelength here is 2L over 3. It's a third of the original. This is the third harmonic. The frequency will be 3V over 2L. If you notice, equation-wise, the pattern looks different from the standing wave on the string, but in terms of equations, they look the same. The fundamental wavelength's 2L, the second harmonic is L, the next one's 2L over 3, so forth. So it turns out that we can say that the lambda for the mth harmonic is 2L over m for the open pipe as well. Just like it was for the string. It works the same. Which means we can also say the frequency of the mth harmonic is mv over 2L. Or it's n times the fundamental frequency. So the same mathematical relationships apply to the open pipe, though the pattern looks a little bit different. Okay. closed pipe is a little bit different. So we have a closed end and an open end. The closed end acts as a rigid boundary. So what that means is as the wave reflects off the closed end, it will invert. What that does to the standing wave pattern is it forces a node to exist at the closed end, but we still have to have an antinode at the open end. So the simplest pattern we get here looks like that. It's still called the fundamental, or the first harmonic. But now, how much of a wave is showing? If we start at the left and go to the right, how much of a wave is that? It's only a quarter. So lambda 1, the wavelength of the fundamental is 4L. It's twice as big as if the pipe was open at both ends.
Is that what a quarter note is?
Quarter note's how fast you play it. So if we have two pipes that are exactly the same length, but one of them has a closed end and the other one doesn't, this wavelength is 2L, this wavelength is 4L. The wavelength's twice as big. So what can you tell me about the frequency? It'll be smaller, but exactly how much smaller?
4 times.
It's half as small as the fundamental.
Half. So this, whatever this fundamental frequency is, this will be half of it. Because 4L is 2 times bigger than 2L. Okay. The frequency required to produce this pattern is the fundamental still. But now it's going to be V over 4L instead of V over 2L. The next pattern, we add in an antinode. So it looks like that. One antinode and then it ends at an antinode. If we start at the left and trace it, how much of a wave is that? 3/4. So that means the wavelength of this one is equal to 4L over 3. So we're going from 4L to 4L over 3, not 4L over 2. This one divided by half to go from one step to the next. This one divides by 3 to go from one step to the next. This is considered the third harmonic, since we divided by 3 instead of 2. It is not possible to get the second harmonic with a pipe that's closed at one end. You just can't do it. So the wavelength is 4L over 3, which will make the frequency be 3V over 4L. The next pattern, we add another antinode. So now, along the length of the pipe, we're seeing 1 and a 4th wavelength. So 5/4 lambda. So that means lambda is 4L over 5. We've divided the fundamental by 5 in the next pattern. This is the 5th harmonic. It is not possible to get the 4th. You sensing a trend? We can only get the odd harmonics if we have a pipe that's closed at one end and open at the other. So if we want to write a generic equation, like we have over there in terms of m's, we can say the wavelength for the mth harmonic We have 4L, 4L over 3, 4L over 5. So we can say it's 4L over M, but M can only be odd. It can be 1, 3, 5, 7, 9, and so forth. It cannot be 2, 4, 6, 8. Cannot be even. So we're restricted in terms of what harmonics we can get. We can get the first harmonic, the third harmonic, fifth harmonic, so forth. If we want to write a generic equation for frequency, it will be mv over 4L. But again, m has to be odd. We can also say the frequency of the mth harmonic is m times the fundamental. That still works. But m has to be odd. Okay, so we're restricted in the m values we can have.
M doesn't really stand for it's just the...
It's the harmonic number, is what m is.
So diameter would affect amplitude and length would affect frequency?
Yes. So the diameter affects how the amplitude of the overall wave, and then the length, since it determines the wavelength, will affect the frequency.
That's how you can tune organ pipes in every instrument.
So for example, one of my favorite open-close pipes, bottle, water. It's the coolest thing. 6th grade we had a water bottle choir. It was so awesome. To a 6th grader. By disturbing air, if I blow into it, I'm disturbing the air in the pipe. This is a closed pipe because I have a water layer here. That water layer is a rigid boundary, so it forces a node. The top, being open, forces an antinode. So it's however long the air column is that determines the note you can hear.
So you add water, you shorten the wavelength.
Exactly. If you add water, you shorten the wavelength. I'm going to get rid of water, so let water out, so that increases the wavelength, makes it longer, which means the frequency has to get lower. The pitch you hear, the lower the pitch, corresponds directly to a lower frequency. Higher pitch is higher frequency. If I get rid of all my water, I get as low as I can with this particular bottle. Okay? Kind of fun. I can't change it now though. Or at least I can't go any lower because there's no way to make this bottle any longer. I could put water back in and shorten it, certainly.
Change the temperature.
Yes, if you change the air temperature, that would change things.
So I know this is beyond like this telescope and what we're talking about, but is the dimensions of the bottle, how it goes narrow to wide and stuff, is that going to change the
The
waves?
pattern will change the amplitude of the wave.
Okay.
So the diameter affects the amplitude. Now there is somewhat of a relationship between the necessary diameter needed and how long the wavelength is. If you've seen an organ, the really long pipes are also really big. The really short pipes are really narrow. There is a relationship between the two in terms of being able to get a good, nice sound out of it.
If you put hydrogen in the bottle or helium, wouldn't the waves be able to travel quicker so you get a
Higher sound.
frequency?
Yeah, so if we were to fill the bottle with a different gas, say helium, and could keep the helium in there, we would get a higher pitch than we would with just normal air. Yes. And that's because the speed would be faster. It travels faster.
So if you wanted to, you could tune your organ by having different gases on each one.
Yes, it might be a little harder to maintain the different gases.
You kill everybody in the church, but it'd be worth it for the sound. You know?
There you go. It's all in the sacrifice of science.
Exactly.
Second one back and then up here.
I just had how is it that the wavelength changes? Because if you have a longer pipe, wouldn't the wavelength stay the same, but you just get more cycles?
The wavelength has to change because of the boundaries. The boundaries force an antinode to exist. So even if the pipe's longer, you're still forced to have an antinode there. But with the fundamental, you can only have one node. And so that's why the relationship, the length is a direct relationship to wavelength.
This is sort of the same.
Sorry.
I was going to say, if you double the length of the pipe, would you go from the fundamental to the second harmonic?
It would still be a fundamental frequency, but it would relate to No, if you double the length of the pipe, you're gonna be at 4L, you're gonna half the frequency. You're gonna, because if you double the length of the pipe, that doubles the wavelength, which will in turn cut the frequency in half. So you're going that way.
How do you get to the second harmonic?
You would have to half the wavelength, would give you a second harmonic.
It's like a recorder. If you go harder, the octave goes higher. So is that the second harmonic?
Yeah, you can certainly force out the different harmonics by blowing differently. Exactly.
So if you blew harder on the pipe or on the bottle, then you'd get the third harmonic.
I don't know if blowing harder on the bottle itself will change it, but
I
I'm not
thought
sure.
was my question. What could you do to get the third harmonic?
I
out of
don't
the
know
bottle?
how to force different harmonics out of this specific bottle.
Well,
But what you
test
can
that.
do, for those of you who are taking lab, you'll do a lab actually. It's not a bottle, but it's a pipe, and you're going to put water in it. You can force the harmonics if you have something out here playing this frequency. So singing or a tuning fork, something like that. If I had a tuning fork that matched this second harmonic frequency and held it over, it would make the bottle sing. It would make the harmonics show up in here.
That's the idea of breaking that crystal goblet with the sound waves. Well, actually, that
That's
breaks-
different.
That's a little different.
Because that's making the actual glass itself vibrate. So in terms of just a bottle, to force the harmonics, you would need something like a tuning fork. Okay. On wind instruments, I know you can affect it by how you blow into it, how hard you blow into it.
Well, like on a brass instrument, it's you change the vibration going into it, changes the pitch.
So,
Okay.
so when a tuba or whatever comes out like this, the amplitude can grow, and that's why you amplify the sound, because the walls are getting bigger.
Well, and it allows the sound to travel in more directions as well.
Okay. But does the amplitude also grow because it's no longer, or does the frequency change because no longer?
I wouldn't expect the amplitude to grow because there's nothing to add energy to
Add
it.
energy, okay.
And so the main part
If you
about having it flare
taper
out.
one of those pipes, you get this big confusion because it would go further to bounce, then come back, and then the wavelength could grow as well as the amplitude,
Well,
right?
keep in mind too that sound, even though I've drawn this as a transverse wave, sound is a longitudinal wave. So they're compressions, so they're not bouncing
So the
necessarily
wall,
off the walls.
however, there is a relationship between the wall and the length, because if you had a really long pipe that was small, you could only get to a certain wavelength, but if you grew that pipe, your wavelength could get smaller, right?
It is the quality of the sound that you can get out of it. The longer the wavelength is, the bigger the diameter needs to be, just to get a nice, good sound out of it. Yeah.
So how does, like a brass instrument, how does that relate when you're going curving around?
It just changes the length.
It just changes the length, it doesn't change the way the compressions go through the...
And it probably affects it somehow, but I'm not exactly sure. But the biggest part is it affects the length itself.